All right. Thank you, everybody, for being here. I appreciate you giving me your time. I hope it's mildly entertaining. So if you've been at this conference, you might have heard the word data. You might have heard it once or twice. I don't know. Everybody's talking about data. They're talking about big data. They're talking about little data. They're talking about shared data. They're talking about integrating data. They're about missing data. They're talking about data pipelines, data, right? What's the big deal with data? So there are a bunch of us who are in the data analytics field, and there's this quote that we kill, okay? There's this gentleman, he's by the name of Sherlock Holmes, and he had this quote that said, "It's a capital mistake to theorize before one has data." And every data analyst has that tattooed to their forehead and then covered over with makeup. And that just says, no theory without data. So that basically sets the necessity of data. Of course, we're all taking our advice from a purely fictional character, but that doesn't matter. So then let's move to someone who's a little more real. There's a man named, I don't know if you know this guy, he's named Clifford Stoll. He was one of the first data forensics experts in the 60s and the 70s. He was known for catching a famous hacker in the 60s and 70s. And when they asked him about how he did it, and they asked him about data, he said, "Data is not information, information is not knowledge, knowledge is not understanding, and understanding is not wisdom." So that's a big way of saying that there's a gap between data, which is necessary, as we know from Sherlock Holmes, and wisdom, which is what we all want. Well, either wisdom or who to start on our fantasy team or our real team. So substitute that for wisdom. So Clifford Stoll said this, and Clifford Stoll, very, very smart guy, but he also, qualifying it, was famous for thinking that the internet would never go anywhere, so you got to take that with a grain of salt. But these two gentlemen, the fictional character and the guy who didn't think the internet was going to go anywhere, basically framed the problem. We have data, which is necessary, and wisdom, which is where we want to go, and we have this chasm in between of how to get between A to B. Okay? And that's what many of us spend hours staring at spreadsheets and box scores and all kinds of programs, basically trying to find a way to cross the chasm between data and, let's say, wisdom or insight. So my colleague, Yuhan Chang, and students at USC, we've been doing this a little while in sports. So last year we did a little bit of work in basketball using optical tracking data. So there's a small summary of the work that we did last year. I'm just going to play that.
In the last decade or so, we've just been able to collect lots and lots of data in places we've never been able to collect before. Now the question is, what do we do with all?
I apologize. This is start that again.
What's happened is in the last decade or so, we've just been able to collect lots and lots of data in places we've never been able to collect before. Now the question is, what do we do with all this data?
I'm sorry, this is the projection issue. Well, I'll try that one more time, and then I'll skip it.
Lots and lots of data. Basketball is kind of a dance. There's always sort of...
So there was basically a video that basically showed, to summarize the work that we did a bunch of work on rebounding, where we looked at the trajectories of rebounds and where they went, and sort of discovered an interesting phenomenon about rebounding and predicted why that happened. And so there was a Hollywood rendition of how we did what we did. And that wasn't the truth. The truth was a lot uglier. We basically took this pile of numbers right here, and we turned it into a paper. And the paper had some interesting things in it. So there was a gap between a pile of numbers and the paper that we produced. And what I want to talk about really is the real path of how we went from the numbers to the insight. So what was the insight? What was the actual process that we did? Not the actual thing that we told you in the paper. So what was the real sort of secret sauce of how we got from A to B? And what does that secret sauce imply, about the future? So I mean, the future is really about how are we going to solve this gap between data and insight. And so there are some prevailing theories as to how you go that way. So one theory is you write a formula, you get some formula, you run that formula over the data, and the output of that formula will give you an answer. And I think we can all see that. And it's a reasonable first pass, but we can all say that probably is not going to be the answer. Well, the other people say, like, well, you can't have a formula, you have to have a picture. You turn the numbers into a picture, and the picture will tell you everything you need to know. And then there's a third class of people like, you can't have numbers, you can't have pictures, they're too simple. You basically have to give it to some gigantic computer. The computer will crank something, and it will give you the answer. So my colleagues and I, we've been working in big data in a variety of domains for a long time. And the answer is because there's this repeated process of interacting with the data, what you really want to leverage is you want to leverage what people are good at and what machines are good at. And you really want to make a system where people and machines work well together. Because that's really the key of solving the problem. So how did this come about? So the example of this is the paper where we said data on the up left and our solution on the up right. And when we write the paper just said, look, we had all this data, and step 1, step 2, step 3, magical insights come out. And that's what the paper tells you. But the real path of getting from A to B looked something like this. And that took a year. And the reason it took a year was because that path was filled with all sorts of roadblocks. You try something, it fails. You try something else, you fail. You try something else, you learn something new. And you have to keep changing and changing and changing and changing and changing. And every step requires a new formula or a new visualization or a new computer running a whole bunch of steps. So basically, the path is filled with all these processes that are going over and over again. So this data analytics is really a microcosm of what one would call the scientific method, right? So basically, you have data, therefore you're allowed to theorize. Then you predict, you experiment, you analyze, and you go through that loop. Now, the key thing that people don't talk about in the scientific loop is there's a key part that's missing, because the key part is repeat. Because it's never a one-pass solution. You've got to go through that thing over and over and over again. And every loop is expensive. And the key is if you have to go through this loop many, many times, and if every path from red dot to red dot is very expensive, it's going to take a long time for you to figure out answers. So really what you are as a scientist or a data scientist is somebody who basically, you have to have a joystick, and you need to be able to sort of move what you're studying. You learn something, you move it, you're just piloting this ship, and the faster and the more nimble your ship is, the quicker you get to an answer. Because you're going to run into dead ends, and you have to recover from them. So ultimately, you're piloting a ship, and the idea is that you want your ship to be like the Millennium Falcon, that you just hyperspace from place to place simply on whim. But we do not have the Millennium Falcon. But my colleagues and I, we've been building a system. We call it Eagle. This is basically has been combining. We were tired of basically spending 1 year trying to get an answer or 1 month trying to get an answer. And we wanted to basically get answers almost instantaneously. So what I'm going to do right now is I'm going to go through sort of a stream of consciousness investigation, okay, and show you that the system should be able to give you those answers as quickly as I am describing them to you. So let's take basketball. So these are some screenshots. So this is basically all, using the stats sport view data. This is every single shot taken over the last 2.5 years on the basketball court. So you can say most of the shots are taken close to the basket, and there's a smattering around the three-point line. You can slice it in a different way to get a higher level picture. That's where the shots are. And you can ask yourself, how likely are they to go in? So you can get a picture of that. This is a sort of a standard picture. Everybody in the field probably knows. If you're not, the reason that the dark green is around the outer ring is its effective field goal percentages, because 3 points are worth 1 point more than 2 pointers, so they get to be colored a little light, darker. So these are standard things that everybody knows. But one of the things that we can look at with this data is we can ask, like, well, how much does the defender matter, right? Because all these shots are completely independent of whether somebody's standing close to you or not. So we started saying, what if we look at the defender distance, and we define somebody, not the closest defender, but the primary defender, because the closest defender could be behind you, and said, what happens when that closest defender gets closer and closer and closer? So you say, okay, what if that guy, the defender, was 3 feet? What if he was 2 feet? What if he was 1 foot away? And then we're looking at this, and we're looking at the question we're asking ourselves is, where did all the shots go? You look at that chart, and it's like, they're not that many, they're all clustered near the middle. So the question is, the first question we came to ourselves when we were just slicing through this data is, where did all the shots go? So we basically made a different way of looking at the problem. What we did was, instead of looking at a standard court grid, which is very natural, we came up with a new view of visualizing the data, where the y-axis is shot distance. So the one near the bottom is stuff close to the basket, and the stuff up is further and further away until you get past the three-point line. And the x-axis is the defender distance. So the bottom left is close to the basket, tight defender. Top right is far away from the basket, and defender far away. So if you look at that and turn to a different view so you can sort of get a little bit more high-level context, This is the landscape of shooting and defending in the NBA. So what is that landscape? So basically, there are two primary modes. People take shots a couple of feet away from the basket, where the defender is a couple of feet from them. And people take three-point shots, where the defenders are apparently 5 feet away from them. So the bulk of three-pointers taken are taken with a defender 5 feet away. There aren't that many tight three-point shots. And then there's this sort of third mode, which is the long two-pointer. And so we've looked at this and sliced it and diced it lots of ways, and basically this curve exists for almost all teams under almost all circumstances, across the board. And we'll go into this in a little bit and what this implies. So you look at that curve. Now, what does that curve tell you about the nature of shooting? So there's an interesting equilibrium here in the game. It's sort of a game theoretic follow-up. If you look at the two shots that were most likely taken, the close two-pointer and the wide-open three-pointer, if you look at the EFG, which is the effective field goal percentage of those shots, and you go back to the numbers, you find that basically those two shots have approximately the same EFG. So there's some equilibrium where basically the best shot that you can get if you execute a good offense, except for sort of a breakdown where you get a wide-open shot, is a shot where you get 54% EFG. And it's a sort of a nice balance between stuff close to the basket and open three-pointers. There's also insight about basically this open two-pointer shot. So that basically is about a 40% shot. And the interesting thing, I mean, clearly you would prefer to have one of the 54s. And I don't know why the person who's shooting a 20-foot shot doesn't step back 3 feet. Maybe there are sort of dynamics for that. We should look into that. But the interesting thing about that is, if you look at this curve, even though it's highly nonlinear, you can see that there's this sort of equivalence class of 40% shots, which makes it basically like it's very hard if you're not going to step back to behind the three-point line to get something better than a long two-pointer, because there's the large equivalence class of 40% shots. To actually sort of get better than 40%, you have to get inside 7 or 8 feet and hope that the defense sags off a little bit. So if you see somebody shoot a long two-pointer, it's not a bad idea unless they would think that they could get from 20 feet down to sort of 7 or 8 very, very quickly while still being relatively open. And then that is generally, I would say, unlikely, especially if the shot clock is running down. So there's this interesting balance, that sort of this interesting phenomenon that sort of developed that has put this picture on the board in terms of shooting. The other nice thing you can see, like when you put the shooting picture up and you also put the EFG picture up, you notice that they're highly nonlinear. They have all these effects. So that also tells you that when you're looking at data, it's very hard to put up a simple formula and sort of extract the meaning from sort of a linear approximation of it, because you're going to lose a lot of the nonlinearity in the phenomenon. So let's see if this really, if this thing really exists. So let's look at shot angle. So let's take the court divided into 6 sectors of 30 degrees. That's what it looks like. So it pretty much looks the same. You can see the only difference is in the far left and the far right angle. The three-point shot is a little further in, because the three-point shot in the NBA court is a little shorter on the sides. Let's slice it up. Let's see what happens in the first or second half. We can re-slice the data, look at it 2 ways, and see that there's not much difference between the first half and the second half. The key thing is not that that I'm using first half, second half, or shot angle. The key thing is that I can slice the data by multiple variables, throw them up there. If I care about other things, if I don't care about first half or other half, if I care about player velocity, defender angle, I can slice them up there, throw them up there, see the picture, get the numbers, and figure out what I want very, very quickly. So the whole key is the slicing and dicing. So let's do because we have optical data, we can figure out all kinds of new things about a shot that we couldn't figure out before. So we can figure out things like, how far away is the primary defender, the shot distance, is the nearest defender, was it a three-pointer, what was the shot type, what was the player velocity? There are all kinds of numbers we can slice and dice the data to. So as a person who wants to sort of swim through data and swim through rapidly, I should be able to ask a system lots and lots of questions and just give it answers to me. So let me just rattle off, if I'm curious and thinking about people taking shots, what are some things I might want to ask about? So let's say, I wonder, if I'm close to the hoop and there's tight defense, who's a really good player? Bang, we have a list. And there's some sense of, there's got LeBron there, Chris Bosh, James Harden, and some other names, and I have a list. But what about close to the hoop and tight defense, but off the dribble? Because a lot of those shots could be, some guy catching it and dunking it. So I only want to know off the dribble. Bang, I have that list. Tony Parker's up there, Monte Ellis, players who make sense. But what about close to the hoop, tight defense, and catch and shoot? How about those guys? Who's good there? Bang. I change a couple of factors. I get the answer right back. And there's our list. Tiago Splitter, surprisingly, #1 over there. But one of the interesting things I noticed, like, oh, look, Tyson Chandler is #2 on this list. He was #1 on this list. Where the heck was he on this list that included everything else? Well, maybe I go into the data. I want to dig a little bit more. What's going on? What's the deal with Tyson Chandler? Well, it turns out there's a third class of ways that you can have a tight shot that's close, and that's anyone? Offensive rebound, right? So they could be tip-ins. So he's good at offensive rebounds, but he loses. I mean, his offensive rebound rate is 52% on tip-ins and sort of shots directly off of offensive rebounds. So that's, even though he's really good at catch and shoots and off the dribbles near the rim, his tip-in rate is bringing him down. So I keep asking questions like, what about, if I have an offense that likes to shoot long 2-footers for some reason, who would I like to have on my team? Well, there's Kevin Garnett and Dirk Nowitzki, and it's not a wonder that the Celtics do a lot of long 2s with Kevin. I mean, he's shooting at 60%, when he's wide open. That's a 40% three-point shooter, so it's really quite efficient. I can look at velocity. Let's say now I'm curious about velocity. I'm wondering about people who can shoot the ball when they're moving very quickly, and other people who can only shoot the ball when their velocity is not very fast. I want to be able to slice the data by velocity and say, okay, who are the best standstill shooters? Does that make sense? Mario Chalmers, Kyle Korver, Tyson Chandler. There's a lot of shots where he's not moving near the basket. So Steve Novak, Matt Bonner. And who are the players who are still really good when they're moving, when they're driving, when they're fading? Tyson's everywhere, by the way. Tyson, you can't get rid of Tyson. I was trying to find a filter where I could get rid of Tyson, but he just can't. But I mean, you can see really like Dwayne Wade, Kevin Durant, LeBron James. So this is interesting, basically, that the ability to shoot. So this basically kind of tells you the ability to shoot while your velocity is high is some indication of how good a player you are. Now, I would be more comfortable about if Richard Jefferson wasn't #9 on the list and Andre Martin was 8, but you don't want to sort of make extrapolations from small sample size. So we can also flip the script. We can flip the script from conditioning on the shooter. We can condition on the defender. So if I want to ask who's the best interior defender, I can look at the EFG of the shooter when a particular defender was their primary defender and get a list of that. Best defender against three-point shots, and on and on and on. And I want to be able to do this Millennium Falcon style, right? That's the idea. Now I'm thinking, I don't want to talk about players. I want to talk about teams. I want the ability to compare situations against other situations. I want to compare teams to teams, players to teams, various types of shots to various types of other shots. I need an ability to do that rapidly, dynamically. So we have a way of looking at that. So this is looking at shooting accuracy. So let me explain this. This is the same graph that we had before. X-axis is shooting distance. Y-axis is X-axis is defender distance. Y-axis is shooting distance. So the red on the right is all the teams. That's the whole league right there. That's the big red thing on the right. The green thing on the left is a particular team. Okay? And the thing in the middle is the difference. And that's shooting accuracy, like basically how well that team shoots for those types of shots with that type of defender distance. And you can tell for this team that for the most part, they generally shoot across the board worse than, this is for data over the last 2.5 years, they generally shoot worse than the league in almost every category. The only time they're better is basically when they're wide open. But this team, if I look at where they shoot the ball, so the far right is the entire league, the far left is in the team, and the middle is the difference. You can see the green areas are where they shoot more and the red areas are where they shoot less. This team is smart enough to know that if I'm going to shoot worse, I'm going to take the shots that matter the most. And the shots they take the most are three-pointers and stuff close to the basket, and the stuff they don't take close are stuff in the middle. In fact, you can see that second square from the top right, that 1.1 is, they're willing to take way more close contested three-pointers than most other teams. Any guess on who this team is? Houston. It's Houston. So, but this is all shots. This is an instant in time. Maybe I want to analyze movement. I want to ask the system, you know what? I'm curious about screens in a particular game. Give me a game. Give me every screen in that game. Okay? And I want to be able to happen in a couple of seconds. Looks like none of my videos are working. But basically, If you had clicked that, you would see that basically you would be able to see every single video in this game. Now, every single screen that was shown in this game, and if you clicked on that button, and I'd be glad to show you after the talk, or right here, that you would be able to see every single screen displayed optically. And similarly, there are things we can do with rebound rates where we're able to play play a team moving dynamically, and for every second in time, we can give every single player the likelihood that they will get a rebound as they move. So you basically have a dynamic system that basically changes every single second when it updates their rebounding probability. So this basically lets you look at things as they're changing in time, screens, movement, and analyze things like crashing the boards or who's able to sort of capture rebounds very, very well. So the bottom line for all the steps is time, right? It's the repeat part of the scientific process. It's the going from roadblock to roadblock. And the question is, we don't want that to be 1 year. We don't want that to be 1 month. We don't want it to be 1 day. We want it to be on the order of minutes, if not seconds. And when is this going to happen? When we can do everything I showed you in the same amount of time it actually took you to talk about it? Well, that moment is actually now. So if you came up to me after the talk and said, show me all that stuff, I could boot it up and basically show you all that stuff in the same amount of time it took me to talk about it. And the reason right now is there's a convergence of basically computation and distributed computing and AI and analytics that really makes, the evolution is at the point where we're right at the tipping point of being able to do this, where people who are not experts in computer science can actually interact with the data that they really want to do, where computer scientists give you the bridge to walk back and forth between the data very, very quickly. So my time is up, so I think I'm going to, there's another video that won't play, but I'd be glad to tell you about it afterwards. It's kind of cool. And so I just want to end thanking all my colleagues who contributed to this work. So.
Thanks, Rajiv. So we have some time for questions, as usual.
I was wondering if there are any players that you found as you were looking through this data that conventionally were not as highly regarded as you would have initially thought, and then they came out higher when you looked.
Yeah, it happens all the time, and that's the funnest part about this. It's like you make these lists. I mean, again, I'm never a proponent of doing something like this and believing that the answer is true, but it gives you a hint, right? So I don't want to give away any answers, but apparently, I didn't know this. Toronto has a guy named Alan Anderson, who's apparently quite a good perimeter defender. I didn't know about him, but I went and looked him up, and we were doing some list. I was trying to figure out who good perimeter defenders were, and I recognized almost everybody on the list, and there was this Toronto player right at the top, and it's like, wow, who is this guy? And so things like that pop up. Now that doesn't mean that I'm going to go say he's the best perimeter defender in the world, but then it sort of gives you a hint, like, who is this guy? I had never heard about him. Let me go look up some tape on this guy. So it has the ability to sort of uncover these little nuggets that, I mean, certainly I didn't know. I'm sure everybody in the NBA already knew about this guy, but for me, it was a revelation.
My problem I always have is if you're looking at the current season, at what point is there enough of minimum data that you can finally see this happening?
Right. So I think that so there's always a balance between sample size and conclusion, but I think when you're dealing with data, you never want to be the kind of person who basically says, if I have enough numbers, I will just believe the answer. You want to have some sense about you. It's like, if there's enough sample, it gives me a hint of something that might be true. I'm going to go to other sources. I'm going to go to my scouts. I'm going to go to my coaches. I'm going to go to the video and verify it. Data has a way of uncovering possible truths, not delivering truths. It's about uncovering possible truths that you can go investigate and possibly find. So that's what I find is sort of the real value of data, is basically discovering things that might be true. You still have to go do your due diligence. Here's the interesting thing about sample size. Okay, there's a slot aside. Like, if there's a coin that's a 51% coin heads and a coin that's 50.5% heads, if you flip those coins like a billion times, you get statistical significance, right? That does not mean that the coins are significantly different, right? So there's a difference. There's actually some power in small sample size where if you get differences with small sample size, it's actually more powerful than actual sort of traditional statistical significance. It goes back to the answer of you should really use data as a divining rod, not as the solution, right? If you start using data as the you put blinders on and you just go forward, you're going to get in trouble.
At what point, I guess, can we tag these stats with videos? For example, you show that Tyson shoots the best off the dribble, but I'm sure those shots were usually two hand dribbles, not one hand dribble. So I guess, how can we, really back up the stats with what we see in these systems we're going to make? So
that's not already far away. I think that's just a matter of engineering right now. I don't think that's a matter of a technical point of view. In terms of like, if there are ways to sort of line up, if you could line up shot clocks. There's a little bit of noise, but in the sense that you could get pretty high level lineups where you say like, here is a piece of optical data, an optical possession, here is a video possession. Lining those up to be roughly close is not, I don't know if it's necessarily solved today, but it's not something that, it's not like, growing a third year. It's something that we can do within the next couple of years, I think.
We have time for one more question. Oh, you're asking now.
So you talked about actual significance in your comment, and in the medical field, we always talk about clinical significance. So how much better does it have to be? So just like, for example, what is a clinically significant, like effective field goal percentage? And can the data that you have right now, solve that problem? How much better does somebody need to be to pay them an extra $500,000 a year, or $1.5 million a year, something like that?
Right. So I think there's separating two things. There's sort of finding an answer to a question and putting a value to that answer. I think putting a value to that answer is totally going to depend on the team, their budget situation, what kind of offense they're trying to run. So that's completely going to be customized to the user, right? So I can tell you that I can give you a widget that's going to make your washing machine half as loud, and to different people that's going to, the widget might be right, but to different people that's worth a different dollar value based on what they do with their laundry. But so the idea is that basically the same thing matters different to different people. So what you really want to do on the data side is you want to give them the answers that they can take and make their value judgments on. You want to make your value judgments on as accurate of ground truth as possible, right? So what we're really trying to do is we're basically watching a game, and over time, we're basically getting different degrees of ground truth. So in the box score in basketball, you're getting hundreds of events a game. In optical data, you're getting millions of events a game. That just means there's more ways to go wrong, but there's a lot more good stuff in there too. So if I give you better ground truth, and for whatever that means, then basically teams are able to it's still their job to put valuations on these things, right? I'm not going to go tell somebody like, okay, it's 0.10, a 10% improvement in EFG, pay the guy $1 million, right? Yeah, it depends on if that's valuable to your strategy or not.
All right, let's give him a round of applause. Thanks, Rajiv.